Welcome to today's paper reading. Today's paper is titled Hyperbolic Entailment Filtering for Underspecified Images and Texts. This paper was published on AR14 by Wonjae Kim and colleagues from NAVAI Lab. The abstract introduces the hyperbolic entailment filtering (HYPE) methodology, which uses hyperbolic embeddings and entailment cones to extract meaningful and well-aligned data from extensive, noisy image-text pair datasets. This approach focuses on enhancing the specificity of each data sample. HYPE shows significant improvement in filtering efficiency and sets a new state-of-the-art in the datacomp benchmark. Additionally, the image specificity I can be used to create an image-only dataset, showing superior performance compared to datasets induced by CLIP score. The performance of a machine learning model is significantly influenced by the scale and quality of the training dataset. High-quality, human-validated data generally leads to better model performance compared to datasets of the same size but with noise. However, the process of creating such high-quality datasets is labor-intensive and costly, making it impractical to scale up. As an alternative, researchers have explored scaling up noisy data, but this approach requires handling billions of data points, which introduces challenges in computational costs and storage. To address these issues, researchers are developing inexpensive automatic data filtering methods for large-scale noisy datasets. These datasets, often sourced from web-crawled documents, use various heuristics to reduce size, such as model-based filtering techniques like those using the pre-trained CLIP model to verify semantic alignment between images and texts. Figure 1 illustrates the application of HYPE filtering on the datacomp small pool. HYPE employs both unimodal specificity, measured by text specificity T and image specificity I, and cross-modal similarity, which can be assessed using either the CLIP similarity cos, theta, or the negative Lorentzian distance minus dl. This approach effectively identifies and eliminates image-text pairs that suffer from misalignment or underspecification issues, which are common in noisy datasets. The figures AC demonstrate cases where image-text pairs show high alignment but are flagged for exclusion due to insufficient specificity. Specifically, B shows low image specificity I, C illustrates low text specificity T, and A indicates low specificity in both aspects. Conversely, figure D presents a scenario with high I and T but low cos, theta, indicating a misalignment between the image and text, as evidenced by the absence of an elephant print in the image. Hyperbolic embeddings are used in this paper to capture additional information, such as specificity, that Euclidean embeddings cannot. In hyperbolic space, more generic data is mapped closer to the origin, while more specific data is mapped farther away. This concept is implemented practically using the Poincaré ball model, which distorts distances in Rn. This model has been extended to image-text contrastive models, showing improved performance in cross-modal retrieval tasks. The datacomp benchmark is introduced as a data-driven evaluation tool, where the size of the model and the number of training steps are controlled and fixed. This benchmark includes 4 different scales of datasets, ranging from small to large, each with a fixed training method and evaluation protocol. The method presented in this paper uses hyperbolic embeddings to capture more complex semantic relationships between images and texts. Unlike Euclidean embeddings, hyperbolic embeddings allow for different distance metrics at each point, which helps in representing more generic data points closer to the center. The authors introduced specificity scores for images and texts, which are based on the average entailment loss. The HYPE score is a combination of these specificity scores, the hyperbolic distance, the cosine similarity from CLIP, and an ImageNet clustering filter. This combined score is designed to improve the filtering of datasets for image-text contrastive learning, leading to better alignment between images and texts. Figure 2 provides a conceptual comparison between Euclidean embeddings and hyperbolic embeddings. In Euclidean space, as shown in A, the dog and cat photo is mapped to the midpoint between the embeddings of a dog and a cat. This is because the photo should be matched with both dog and cat embeddings. However, this mapping does not fully capture the complex semantic meaning. In contrast, hyperbolic embedding space, as shown in B, can represent more complex information. It maps more generic data points closer to the center point in hyperbolic space. For instance, the textual embeddings of a cat and a dog are closer to the center, animals, than that of a dog and a cat and cats and rats. This property allows hyperbolic embeddings to capture additional semantic nuances that Euclidean embeddings cannot. Figure 3 presents examples of low and high specificity values, INT, from the 12.8 m datacomp small pool, divided into percentile groups with 20% intervals. Higher values indicate greater specificity. For texts, the lowest T values correspond to empty sentences or very general text like picture, while higher T texts are longer and more detailed. For images, low I values are associated with background images or those with too many objects, whereas high I images are iconic, containing a single object that can be precisely described. Figure 4 provides a visual explanation of the APER equation, ECN 5, the EXT equation, ECN 6, and the entailment loss equation, ECN 7. These equations are crucial for understanding the hyperbolic trigonometry involved in the relationship between image and text embeddings. The figure illustrates how the acute angle between these embeddings is calculated, and how the entailment loss is determined by the difference between this angle and the size of the cone. This visual aid is essential for grasping the mathematical underpinnings of the hyperbolic entailment filtering process, which is used to measure unimodal specificity independently. Figure 5 presents a comparison of HYPE with baseline filtering methods, focusing on the performance of models trained on subsampled datacomp training sets ranging from 10% to 40%. The evaluation spans 4 datacomp benchmark task groups, with each model being trained 4 times using different seeds. Notably, the 10% and 30% results are consistent with those shown in Table 4. The figure highlights that HYPE consistently outperforms the baseline methods, demonstrating its effectiveness across various sample sizes and task groups. This superiority is particularly evident in lower sample sizes, 10% and 20%, where the filtering effect is more pronounced, resulting in larger performance gaps compared to the baseline methods. Table 1 presents the statistics of the datacomp dataset, which includes fewer samples than the original release due to inaccessible URLs. The table shows that the overall metric statistics remain largely unchanged for both small and medium scales. Key metrics include the dataset sizes, T, text entailment, and I, image entailment. Notably, T is significantly lower than I, indicating that text always entails an image empirically. This suggests that using these metrics for filtering will yield similar results even when the scale exceeds datacomp medium. Table 2 presents the zero-shot classification accuracy on ImageNet 1K and the text-to-image and image-to-text retrieval recalls on MS COCO for CLIP and Meru models. The results indicate that Meru outperforms CLIP in several key metrics, such as IN 1K accuracy with 42.3% compared to CLIP's 37.9%. In COCO T2I retrieval, Meru achieves a significant improvement with an R1 score of 30.2% versus CLIP's 15.4%. Similarly, in COCO I2T retrieval, Meru's R1 score is 43.3%, surpassing CLIP's 21.2%. These findings suggest that Meru's performance is superior in both classification and retrieval tasks, highlighting its effectiveness in zero-shot learning scenarios. Table 3 presents an ablation study of the HYPE method, focusing on the impact of each component on performance. The study reveals that while the CIN component enhances zero-shot performance on the ImageNet dataset, removing CIN results in superior average performance across datasets. Notably, the model trained with significantly fewer data points and seen training samples outperforms the OpenAI CLIP baseline. This suggests that the HYPE method's design allows for efficient use of data, potentially reducing the need for extensive training data. Table 4 presents a comprehensive comparison of the hyperbolic entailment filtering for underspecified images and texts, HYPE, method against concurrent works that challenge the datacomp benchmark. The table includes methods such as CLIP-L/14, WS, TMARS, CIDS, and DFEN, with HYPE being evaluated at different sample sizes ranging from 1.2 million to 38 million across datacomp's small and medium scales. Each method's performance is measured across several key metrics: ImageNet accuracy, ImageNet distribution shift, visual task adaptation benchmark, VTB, retrieval performance, and an average score. The table highlights the best and second-best scores, providing a clear view of Hype's competitive edge in the image-text contrastive learning domain. In this section, we discuss the comparison methods used in our study. These include simple baseline filters such as language, text length, and image size, as well as more advanced methods like image-based clustering and clip score filtering. Moving on to image-text contrastive pre-training, our results show that Hype significantly outperforms other baselines. This is attributed to the effectiveness of hyperbolic embeddings in improving retrieval scores. Additionally, Hype can be combined with other methods to further enhance performance. Lastly, for image-only contrastive pre-training, we apply eye-based filtering for self-supervised learning methods. This approach consistently outperforms the traditional cos, theta, method, leading to better SSL performances. Figure 6 illustrates the relationship between the zero-shot accuracy of filtering networks and induced networks, as described in the Defend paper, 19. The figure shows that a better-performing Meru model consistently results in a more effective filtering network, indicated by improved zero-shot accuracy. This upward trend suggests that further enhancements in Meru could lead to even more effective filtering, which is not observed in the downward trend of Euclidean clip. Additionally, the image specificity metric, I, is shown to efficiently identify iconic images, which is significant for image-only self-supervised learning methods. Table 5 presents the ImageNet 1K linear probing classification accuracies for the Vision Transformer Small (VTS) model, comparing two filtering metrics, cos, theta, and I. The dataset used is the datacomp medium, which varies in size from 0.13 million to 1.28 million images. The self-supervised learning methods evaluated are SimCLR and MoCo V3. The key findings show that I consistently yields higher accuracies than cos, theta, across all dataset sizes. Notably, MoCo V3 trained with datasets filtered by I outperforms SimCLR trained with datasets filtered by cos, theta, for most dataset sizes. This suggests that the choice of filtering metric can significantly impact the performance of self-supervised learning methods, with I providing a more effective filtering approach for underspecified images. In this paper, the authors discuss the limitations of their method and propose future research directions. One significant limitation is the absence of larger datacomp subsets in their experiments. Given Hype's increasing performance gap as dataset size grows, it is hypothesized that Hype could perform exceptionally well on these larger datasets. Additionally, the hyperbolic clip size was set to L/14, which aligns with datacomp standards, but a larger architecture could significantly enhance performance. The research also used only I to create an image-only dataset, suggesting that using T to generate a text dataset could create a visually meaningful corpus, potentially aiding in training a language model that adapts quickly to visual inputs. Finally, the authors recognize the potential for extensive ablation studies, particularly regarding the coefficient used in merging metrics for Hype, which could provide deeper insights into the model's behavior and performance, thereby enhancing its overall efficacy. In this section, we will briefly review some key references that have contributed to the field. First, Hyperbolic Image Segmentation by Meena Gadamiatai et al., presented at the IEEE/CVF Conference on Computer Vision and Pattern Recognition in 2022. This work focuses on segmentation techniques in hyperbolic space. Second, Modeling Heterogeneous Hierarchies with Relation-Specific Hyperbolic Cones by Yusher et al., published in NeurIPS 2021, which introduces methods for embedding hierarchical data in hyperbolic spaces. Lastly, the second Pascal Recognizing Textual Entailment Challenge by Roy Barhayam et al., from 2006, which addresses the challenge of determining whether one piece of text entails another. In this study, we analyze four primary metrics: text specificity, T, image specificity, I, negative Lorentzian distance, -dl, and clip cosine similarity, cos, theta. We present histograms for each metric to illustrate their distribution across different subsets of the datacomp medium data pool. These subsets are color-coded for clarity. Defin is shown in blue, CIDS in orange, our method, Hype, in green, and the no filter condition in red. We also highlight the average values for each metric with vertical dotted lines in their respective histograms. Each method results in a different amount of data in the subset, so for ease of comparison, the y-axis shows the relative percentage rather than the count. Thank you for watching.